Imagine machine elements that could talk. Well, not in words, but in data. If you take a look at this slide, gearbox is full of such components, each of them potential source of valuable information. There are parts for shaft type connections, like quadricles, spline shafts. There are different kinds of bearings. There are parts for connection sealant purposes, like screws, rotary shaft seals. And there are parts for power transmission, like gears and couplings. Imagine these machine elements could tell you how much they are loaded, or what they are, or even when they are prone to failure. This is what we are working on in a DFG program, turning standardized machine elements with a space-neutral design approach into sensor-integrating machine elements. My colleagues and I at the Dresden University of Technology are working on creating a sensor-integrating jaw coupling. Jaw couplings are widely used components of drivetrain assemblies. They connect two shafts together in order to transmit power and also to compensate for shaft misalignment. With this coupling, our goal is to measure the rotation speed, the transmitted torque, and its current temperature. And we think with this data, there's a wide variety of applications that arise. For example, we can create a condition monitoring system based on this data, or even a digital twin of a drivetrain, or together with other sensor integrating machine elements, a digital twin of an entire machine. However, from an engineering point of view, knowing the transmitted torque is often only part of the picture. Because if misalignments are present, loads not only for the coupling itself, but also for the surrounding machine elements can be significantly increased. Therefore, we ask ourselves, can we use the sensor integrated jaw coupling to also detect shaft misalignments? And in order to answer this question, I want to present to you our measurement chain and the structure of our sensor. I will then briefly present our experimental investigations and the results that we found. So starting with the measurement chain. Here you can see a render of our current prototype. We only modify this elastomeric gearing here in yellow by introducing a cavity into each tooth of the gearing. Inside this cavity, a dielectric elastomer sensor, this black part over here, is placed. We then seal off the cavity with two strain amplifiers made of hardened tin. Now, if a torque is applied to the coupling, depending on the load direction, the teeth, the odd or even teeth, will deform. This deformation is then transmitted via the strain amplifiers onto the dielectric elastomer sensor. Here you can see one of our sensors that my colleague is manufacturing. These sensors internally basically behave like plate capacitors. So if they're compressed, the capacitance will change. And we use this capacitive change together with a sophisticated regression model to then approximate the transmitted torque. Additionally, we want to send out wirelessly Bluetooth low energy the current rotational speed and the temperature of the coupling. However, creating this regression model is quite a complicated task, and we want to build upon a rich database to tackle this. This is complicated because the material of the gearing has thermoviscoelastic properties. That means you need to know the current temperature and the deformation history of the gearing in order to predict the transmitted torque correctly. And we're gathering the data for this with intensive finite element simulations and experimental investigations. Now, with this in mind, let's take a closer look at the sensor. Our sensor is basically capacitor. So we start with a layer of elastic which conductive ink is applied. This forms the first capacitor plate. Now we apply a layer of adhesive, which is a very soft Ecoflex. So one of the presentation, this is in micrometers. And then another layer of elasticity is applied on top of this. Then we turn the stack up around, apply another layer of conductive ink and adhesive and elasticity. And now we have formed our first capacitor. Then we take these elements and stack them on top of each other until we reach the desired height or capacitance of the sensor. In the end, the sensor is sealed off with two buffer layers in which a groove is engraved. Inside this groove, we place a conductive thread, which is used for the interconnection to the capacitor plates and also to connect to the sensor inside the coupling. Now, let's take a closer look at the experimental investigations. Starting with the test bench, you can see an image of our test bench. In the center, we have the sensor integrated draw coupling that is connected to two shafts. On the right side here, this hub will be radial displaced with a fine threaded screw. Note that we measured radial displacement with two dial indicators very close to the gear in order to account for the flexing of the shafts and bearings during the misalignment process. If we take a look at the sectional view of the coupling here, you can see the numbering of the teeth and in which direction radial shaft misalignment was applied. Additionally, I want to introduce C, which denotes the current rotation angle of the coupling. Now, let's take a closer look at the results. Here you can see the capacitive change of each sensor over a rotation of the coupling with no misalignment is present. And we can see here that the capacitive change is close to zero. However, if we apply radial shaft misalignment, in this example here, 400 micrometers, we can see that we get a sine wave response from each sensor, and that there's a 45-degree phase shift of each sensor's maximum. And this correlates to the geometry of the group. Now, in the next plot, I've split the data into odd and even teeth, and we basically now follow the sensors point. And here we can see that the data points are averaged of the sensors and from two measurements. We can see that clearly with an increase of the shaft misalignment, also there's an increase of the amplitude of the capacitive change. This indicates that we have good sensibility of the signal. Now, if we take the data from the white plot and visualize it in a polar plot, we get something like this. Remember, we applied the misalignment in a 0-degree direction. And we can see that depending on if we're looking at the bottom of the teeth, there's always a specific phase shift here. So now, if we know where the coupling is located, we could even tell which direction radial shaft misalignment is applied. This is quite a neat feature because during this alignment process of drivetrains, this is something that requires a lot of knowledge and time from technician. So, with additional data, we're also able to detect the direction. Okay, but can we approximate the misalignment? My colleague previously did simulations regarding this topic and came up with a simple equation. The equation takes a W, which denotes the normalized capacitive amplitude over rotation and the current maximum deformation angle between the hubs. And we basically used this formula and plugged it into experimental data, and the results you can see on the right side in the parity. It is evident that we are quite close with our predictions with applied misalignments. However, we can also see that the errors are still quite high. And this is due to the sensibility of the sensors. Due to the manual manufacturing process, we have varying capacitance of the sensors, which is a problem. However, we're still able to approximate the radial shaft misalignment even using the simulation. Now, with this results in mind, let's return to the best restart. Can we use sensor integrated draw coupling to detect shaft misalignments? Well, basic or short answer is yes, but there's some caveats. We've seen that we have an experimental proof of the concept and we have good sensibility of the signal. And together with additional data, we're also able to detect the direction which the misalignment was applied. However, we've also seen that there are still some deviations in sensor sensibility, which we currently are actively working on. Additionally, we're currently building a new test bench, which we can also test the coupling in a rotating way with varying shaft misalignments to investigate this. We think with this better data, we can increase the reliability of formulas and also increase the approximation accuracy of the transmitted term. With this, I want to thank the German Science Foundation for the funding and its great collaboration. Thank you.